Hello and welcome to the Chemistry Made Simple podcast. I'm your host Matthew Macario, and this is the podcast where you get chemistry confident and go from point A to grade A. Hello, welcome back. How are you? This episode considers the reactivity and reactions of alkenes. So in this episode, we'll be looking at the functional group within the alkene, the double bond. We'll be looking at the type of reactions that alkenes undergo and describing how it works. And we'll also be introducing the concept of electrophiles and defining what they are too. So when we consider the reactivity of alkanes and their reactions, we need to think about the functional group that makes a compound an alkene. And we covered this in our last episode where we introduced the alkenes. You'll recall that alkenes are defined by the fact that they have a carbon-to-carbon double bond. And we also mentioned that counterintuitively, this is the centre of where reactions occur within an alkene. Why is that counterintuitive? Well, you would think a double bond would be much stronger than a single carbon-to-carbon bond. It is much stronger, and therefore you might think that that would make that part of the molecule the least likely part of an alkene to react. There does seem a little bit of logic behind that, but there are good chemical reasons why that's not the case, why that double bond region of the alkene is the heart of where most reactions occur. The key reaction we're going to talk about in today's episode is electrophilic addition. Let's break that down a little bit. So we use the word addition in the name of that reaction, and as you would expect, that means that we're adding something to the molecule, not substituting and not removing something, but adding something. And the other word we use was electrophilic. That's because the alkene reacts with an electrophile. What's an electrophile? Let's break down the word. Electrophile literally means an electron liker or lover. An electrophile is something that is attracted to, electrons are attracted to negative charge. And the double bond within an alkene is an electron-rich area. Therefore, that region of the molecule has a higher density of negative charge. There is more electron density around the double bond in an alkene than in the rest of the molecule. So an electrophile, something attracted to negative charge, would be attracted to that part of the molecule. So what examples would there be of electrophiles? Well, electrophiles must be atoms, ions, or molecules that are able to accept electrons. Therefore, they're attracted to electrons. A hydrogen ion, H+, would be an excellent example. It's possibly the most common electrophile that we'll come across. Polar organic molecules, molecules with a polar bond in them, will have an electrophilic region of that molecule. Within that molecule, the atom that has lower electronegativity will have electrons drawn away from it by the atom that has the higher electronegativity, therefore making the atom with lower electronegativity electron deficient. The molecule remains uncharged, but the charge, again, isn't evenly spread. We often label the electron-deficient atom with a delta plus, and any molecule that has an atom with a delta plus, that part of the molecule may be attracted towards the double bond of an alkene. So if we think about the molecule hydrogen bromide, for example, the bromine atom is much more electronegative than the hydrogen atom, and therefore electrons will be drawn more towards the bromine atom, making the hydrogen atom electron-deficient. Overall, the molecule is neutral in charge. But the hydrogen end of that molecule may well be attracted towards the double bond of an alkene because it's electrophilic. So let's consider the reaction between ethene, an alkene, and hydrogen bromide. When these are reacting together, the hydrogen bromide, as we've mentioned, is an electrophile, so the hydrogen end of that is attracted towards the alkene and towards the double bond. As it approaches the double bond, a reaction begins to actually occur between the two molecules. Just a note here, you might hear that attraction and the beginning of that reaction between the electrophile and the alkene. You might hear that described as the electrophile attacking the alkene, depending on what terminology your teacher or the other resource you're using might want to use. It's quite a common way of describing that attraction and the beginning of that reaction. You don't need to use that word yourself, but you can do. It's generally understood and accepted. Okay, back to the reaction. As the hydrogen bromide is attracted towards the electron-rich double bond of the alkene, there is going to be a reaction start. The first thing that must happen is the bond between the hydrogen and the bromine must break. Both electrons go to the bromine atom, making a bromide ion. Without that step happening first, the hydrogen would not be able to accept extra electrons. But now that bond is broken, the hydrogen has no electrons associated with it. It's a hydrogen ion. And it's considered that immediately one of the bonds of the double bond between the two carbon atoms will break, and both of the electrons form a new bond between one of the carbons and the hydrogen ion. That's all considered to be one step. This has created an intermediate species where we have what was the alkene. There is now only a single bond between the two carbons, and one of the carbons has a bond to the hydrogen that was part of the hydrogen bromide molecule. The other carbon atom has now lost an electron. The electron it had put into the bond between it and the other carbon is now in that bond between the other carbon and the hydrogen. So the carbon that's lost its electron actually has a formal positive charge on it. So overall, this species is a carbocation, an organic molecule with a formal positive charge. There is also a bromide ion hanging around too that was part of the hydrogen bromide molecule. All this is considered the first step of that reaction, of that mechanism. So what's the second step? Well, we have a carbocation, which is not a stable situation, and we have a bromide ion. The carbocation, of course, has a positive charge, and the bromide has a negative charge. And you can probably guess that in the second step, the bromide ion, which is electron-rich, is attracted towards the positive carbon within the carbocation, and the bromine puts both electrons into a new covalent bond between the bromine and the positive carbon. So what's the result after step 2? The alkene has had its double carbon-to-carbon bond replaced by just a single bond. There is a new bond between one of the carbons and the hydrogen, and a new bond between the other carbon and bromine. So we have a halogenoalkane, bromoethane. Just as a side note, if you've been following our series in organic chemistry, this is a second way that halogenoalkanes can be formed. So the second stage brings us to having just one product. Hydrogen bromide has added entirely to the alkene. So we have a completely different, stable product. And that's the end of the reaction for that pair of molecules. The electrophile has added to the alkene. And again, let's talk about some terminology. You might hear it has added across the double bond of an alkene. It's quite common to describe the electrophilic addition to a double bond as adding across a double bond. This kind of electrophilic addition happens with alkenes of all sizes. It can happen with different electrophiles. We talked about hydrogen bromide. We could use hydrogen chloride instead to get a different product. Electrophilic addition can also happen with halogen molecules, such as Cl2 or Br2, can add across that double bond. And in those cases, of course, in the product, both of the carbons that were in the double bond will now be bonded to the halogen atoms. We can also do this reaction with sulfuric acid and an alkene. There is an extra step. We add water after the initial reaction, and we turn the alkene into an alcohol in that reaction. Another electrophile we might use with an alkene is water. That will also successfully add across the double bond of some alkenes. This is usually done under pressure and high temperature. In industrial manufacture, we use ethene and steam to make ethanol. It's another way of making ethanol without having to do a fermentation. Okay, what other reactions do alkenes undergo? Well, we already mentioned in the previous episode that alkenes will undergo oxidation in a combustion reaction in a very similar way to alkanes. And we mentioned that the reason we don't tend to use alkenes as fuels is because they're very reactive and therefore far too valuable for many other purposes. So it would be quite wasteful to use them just as a source of energy. And a further reaction that alkenes undergo is they undergo polymerization to make addition polymers, and we'll cover that in a further episode. So what have we talked about today? We talked about the counterintuitive reactivity of the double bond in an alkene. We talked about electrophilic addition and defined what an electrophile is. We talked about some terminology. So when an electrophile is attracted to an alkene, we might call that an attack by the electrophile. The electrophile is attacking the double bond. We also said that the electrophile can be described as adding across the double bond in an alkene. We talked about the mechanism where the second bond between the two carbon atoms breaks and a new bond is formed between one of the carbons and the electrophile. And the second step being the reaction of the carbocation with the anion that's been formed during the first step. So that brings us to the end of this episode. I hope you found it useful. If you've any further questions on this topic, then please do come and ask them, the best place being in the Patreon community. I'm sure you've already joined. If not, you can sign up very easily at patreon.com/chemistrymadesimple. Patreon is Patreon. While we're talking about Patreon, I want to take the opportunity to thank all the show's patrons, and particularly the latest patron, Ryan Vest. Thank you for supporting the show. It does mean a lot, and it does help keep the show going. You can also find me on Instagram at Chemistry Made Simple and on YouTube at the Chemistry Made Simple Academy. What I would suggest from this episode is to go and review it, do some past questions because it's quite a complex subtopic. I would suggest trying to draw out the mechanism that we talked about in today's episode. And then, of course, I'm looking forward to speaking to you in the next episode. So until then, do look after yourself and goodbye.